programming using equations to model linear data or real-world type problems. This is section 2.4 in your book, chapter 2, section 4. Example 1, Jacksonville, Florida has an elevation of 12 feet above sea level. A hot air balloon taking off from Jacksonville rises 50 feet per minute. Write an equation to model the balloon's elevation as a function of time. So we want to write elevation as a function of time. E of t equals something. Graph the equation. Interpret the intercept at which the graph intersects the vertical axis. So they're saying, tell us what the y-axis, the y-intercept actually means. Alright, so to write a linear equation, you either need 2 points or you need a slope and a point. And in this case, we are given a slope and a point. So pause the video and see if you can figure out what the slope of this equation is. A slope is a rate. It's rise over run, or change in y, that's what the triangle stands for, over change in x. Well, in this case, the y-axis, the vertical axis, is elevation. So we're looking for a change in elevation over a change in time, because the horizontal axis is time. So where does it tell us a change in elevation over a change in time? And it gives it to us in feet per minute. That's here. 50 feet per minute. That's the slope of this equation. 50 feet per minute is the slope. And then this, 12 feet above sea level. That's the other piece of information that it gives us. What does that tell us? Well, it's where it's starting off from. It's going from Florida, right? So at time 0, when time is 0, it's already at 12 feet above sea level. That's a point. It's a point 0, 12, t, e, or x, y. But in this case, our independent variable is t, and our dependent variable is e. So this is the point that it gives us. That point is the y-intercept. So this problem gives us m of 50 and b of 12. So we could write the equation, we can just fill in here. We have a line, elevation, as a function of time is equal to 50t plus 12. However much time in minutes times 50 gives us the number of feet that we've risen in that number of minutes, and then we add it to the 12 feet that we originally that we started at, and that gives you the elevation as a function of time. Okay, example 2. A candle is 6 inches tall after burning for an hour. After 3 hours, it's 5.5 inches tall. Write a linear equation to model the height y of the candle after burning x hours. So y is the height, x is the time in hours. So we want to write a linear equation. I'm going to call it a function height as a function of time. Okay, now to write an equation, you need 2 points or a slope and a point. In this case, we're given 2 points. Okay, so the x value is in hours. So this first one says 6 inches tall after burning for 1 hour. That's giving us the point 1, 6, x, y, hours, height. And then the second one is giving us the point 3, 5.5. From these 2 points, you should be able to find a line. We could use the y equals mx plus b, but I think it's easier to use this. Y minus y1 is equal to m times x minus x1. This is point slope form. I actually shouldn't write this h, t because it tells us to write it in terms of y and x. So here's the equation that we're going to use, and we're going to use these 2 points. Well, I'm going to use 1, 6 to plug in for y1 and x1. And I'll do that now. Y minus y1, the 6, is equal to the slope times x minus 1, that value. Alright, so now all we need to have the equation of a line is the slope. And we can find out the slope using the slope formula and these 2 points. So the change in y is 6 minus 5.5, and the change in x is 1 minus 3. That gives us a 0.5 over negative 2. 0.5 over negative 2, that's the same thing as 1/2 over negative 2, or 1/2 divided by negative 2, which is the same thing as 1/2 times the reciprocal of negative 2, which is 1 over negative 2. And this is equal to 1 over 4, or negative 1/4. This is our slope. The slope is negative 1/4. So let's go ahead and replace the slope here with negative 1 over 4. Here's the equation of our line. Note that this is also the equation of our line. So if you decided to use the second point instead of the first one, you would get this. These are both the same line, and they're both equally correct answers. Example 3. Use the equation from example 2. Okay, so this is the equation that it says we got, but that doesn't look like what we got from example 2. We got y minus 6 equals negative 1/4 x minus 1. So why is it written that this is our equation? Well, they went ahead and wrote it in in slope-intercept form. And I'll go ahead and solve this for y and show you that these are the same equations. If you distribute the negative 1/4, you get negative 1/4 x. Negative 1/4 times negative 1 is a positive 1/4. Now if we add 6 to both sides, we get y equals negative 1/4 x plus 6 1/4. And if I wrote that as decimals, that would be negative 0.25 x plus 6.25. And that's what this equation is. You don't actually need to write it in this form. I'm going to use this form to solve the problem, but I was just showing you that those are in fact the same equation, just rewritten. In how many hours will the candle be 4 inches tall? Remember, hours are our x value, x is in hours, and height, y is the height. Hours and height. So when they give us this value 4 inches tall, that is a y value. So I come over here and plug it in for y. And now I'm going to solve for x. 4 minus 6 is 2. Distribute that. Negative 1/4 x plus 1/4. Subtract 1/4 from both sides. I'll write this over here. You get negative 2.25, or negative 2 1/4, is equal to negative 0.25x. Divide both sides by negative 0.25, and you get x is equal to 15 hours, I think. No, that's not right. 25 goes into 200 8 times, so it would be 9 hours. Negative 2.25 divided by 0.25 is 9 hours. Okay, if we had done this with the equation that they gave us, it would have been a bit easier because they had already done a few of the steps for us. And I'm going to go ahead and do that really quickly. You can skip ahead if you'd like. So y equals negative 0.25x plus 6.25. If you plug in 4 for y, you have this equation. Subtract 6.25 from both sides. You get negative 2.25 equals negative 0.25x. You do the division again, and you see x equals 9. Okay, now we're going to talk about scatter plots. That's what these are. So you can imagine there's a y-axis here and an x-axis here, or maybe it goes like this. But these are in the coordinate plane. We're going to talk about a concept of correlation. This is actually something that you'll study in statistics if you take that class, and you'll talk about it more specifically. Correlation is actually a number that you calculate, but for our purposes, we're just going to talk about which direction the scatter plot is going and the relative strength of the scatter plot. So if you look at this one, there's definitely a form to this scatter plot. You could draw a line right through it, and it would get close to most of the points. Over here, there's also a form. You could draw a line through it, but it doesn't get close to a lot of the points. Over here, there's kind of a form, but a lot of the points are pretty far away. This one, I can't really tell if I should draw a line here or here, which one would be better. It kind of looks like here, but actually it's the same. in either case. So that's why this one has no correlation. It would be equally correct to draw a line anywhere, and actually it would probably look something like that, the line. So no correlation. Correlation is related to the slope of the line. Okay, so this one has no correlation. This one, there is a form. It goes down like this. This is why it's called negative correlation, because the slope of this line would be negative. As it goes farther to the right, the graph goes down rather than up. And it's also a weak correlation. The points are pretty far from that line. Over here, it's also weak because the points are pretty far from the line. It's a little bit stronger than this correlation, but it's still weak. The points are closer to the line than they are here, but it's still weak. It's positive because the slope of this line would be positive. Here, you're getting closer. Okay, so this would be called moderate. The points are closer to the line, and then they're negative because the slope of the line would be negative. Here, this is pretty strong. The points are pretty close to the line. All the points are close together, and then it's positive because the slope of that line would be positive. And then here, if you were to draw a line right through it, this would be really strong because all the points are very close to the line, and it's negative correlation because the slope of the line goes down. These lines are called trend lines. And there are a bunch of different types of trend lines, but the most common is called the least squares regression line, and that's what we're going to use in class in an activity. But yeah, so trend line is the line that goes through and kind of models the scatter plot that you're looking at. So let's go ahead and make our own scatter plot from this data and then decide whether or not a linear model is reasonable. So X, this is number of years since 2000, or actually, sorry, since 1999. That's kind of strange. Oh, it's because that's what she's interested in the problem. And then Y is the price of the car. Y is money. Okay, so this first one, 2000, that should be 1. It says use 1 for 2000. So at 1, we have 2 points, 5,784. And this is 4.5. That's a weird scale. Okay, so we have 2 points about right here. I'm going to use a smaller pen so that I can draw them more accurately. The next year we have 6,800. So this is 7.5. So 6.8 is about here. 6.2 is going to be about there. So I'm going to go ahead and finish plotting all of these. Go ahead and pause the video and try and do the same. Okay, so here are all of my points. Again, I apologize for the kind of crazy scale that I have here, but these are the points plotted. And it says, so this is our scatter plot. Decide whether a linear model is reasonable. A linear model looks like it's reasonable. I could take a line, let me get one of my line tools, and I could go through here, and that's pretty good, right? I mean, all the points are pretty close to it, so I could use a line to represent that data pretty well. So it says draw a trend line, write the equation of the line, and determine whether the asking price is reasonable. What was the asking price? I don't see an asking price. Okay, so we'll I didn't write that information down here, but so we're going to draw a trend line, which we've already done. We're going to write the equation of this line, and then we're also going to determine what would be a reasonable asking price for the year 1999. Okay, so where is this crossing? So to write the equation of a trend line, we need 2 points or 1 point and a slope. I'm going to go with a point and a slope. So here, it looks like this is crossing the x-axis at about $3,800. So that's going to be our b value. We're going to write it in this form, y equals mx plus b. So our y-intercept is about 3,800. So now we have mx plus 3,800. Let's figure out our slope now. Okay, slope means for every 1 that the x goes over, how far did you go up? So from here, if I go over 1, it looks like I'm up at about this is 4,500, this is 6,000. It's right in between those 2 points, which were here, so I'm going to say 5,600. Okay, so it looks like my slope is about approximately 5,600. I can also look for a place where it goes through a point right here. No, I'm just going to use that. Okay, so it goes from here, which was 3,800, up to here, which is about 5,600 in 1 year. Okay, so my slope is going to be about 1,800. Okay, it goes up about 1,800 in 1 year. So I could say my slope is 1,800 over 1. Okay, that's what my m value is. So let me erase that, and I'll just write 1,800. Okay, so my slope is about 1,800. This is a pretty good trend line. And then to answer the second part of the equation, the question, so I'm going to write that over here. Here's our trend line, 1,800x plus 3,800. Determine whether the asking price is reasonable, or a different way to say that is, what asking price would be reasonable for 1999? Well, 1999 is represented by 0 on here because we had years since 1999 as our x-axis. So at 0, when x is 0, this term goes away, and y is 3,800. If you come back over here, you can see when x is 0, we crossed at 3,800, our y-intercept. So about $3,800 would be a reasonable asking price for the year 1999. So that's where linear models are kind of useful, because you can extrapolate just a little bit. Extrapolate means make a guess on either side of your data, and get a pretty reasonable answer. Okay, that's it for this lesson.